Welcome to iTTV for Form 5 Physics. The title of this lesson, Interference of Waves. In this lesson, we want to have a look at interference. Interference occurs when two waves move towards each other and then cross over each other. When this occurs, two possible things can happen. Either the waves will interfere constructively or they will interfere destructively. If you get constructive interference, what happens is that the waves' amplitudes add up and become larger. Either your crest will increase in size or your trough will increase in size. Size here meaning the amplitude. If you have light, what will occur is the light will become brighter or the light will become darker, depending on whether or not we have constructive and destructive. And with sound also we have this interference, where the sound will become louder or softer, depending on whether we have constructive and destructive. Later on we want to have a look at maybe one or two applications of interference in our daily life. So let's get right into this lesson. How does interference occur? A crest superposes a crest. The displacement of the resultant wave is the sum of the displacements of individual waves at every point. A trough superposes a trough. Once again, the displacement is the sum of the displacements, and the displacement in this case is negative. Interference of waves. Consider two pulses of the same amplitude propagate in different directions along the same medium, and each crest has an amplitude of A. So here we have two pulses that are moving towards each other. Let's sketch this on the board so that we can go through it step by step. So let's say one pulse is coming from left to right. So let's draw this pulse up here. It's going from left to right and it has an amplitude A. Let's say that another pulse is coming from the right to left direction, also of amplitude A. Now at some point these two crests have to meet each other, and when they meet each other, the final displacement will be the sum of both their displacements. So when they meet each other, you will get this occurring, where your amplitude becomes 2A. And then after that, the waves will continue on in their normal direction. This pulse will continue on moving this way, and this pulse over here will continue moving on its merry way, their amplitudes back to the original amplitude of A and A. Now when you get interference such as this, where your amplitude is increasing and you get similar parts of the wave meeting, meaning that they are in phase, so you get a crest and a crest or a trough and a trough, we call this type of interference constructive interference. So if you get a crest plus a crest or a trough plus a trough, what we get is constructive interference. So this gives us constructive. Okay, so this is constructive interference. So let's go back to the slide. As the crests move towards each other, there will eventually be a moment in time when the two crests are completely superposed. At that moment, the resulting shape will be a crest with amplitude of 2A. This is called constructive interference. A crest superposes a trough, waves arrive exactly out of phase. The crest of a wave meets the trough of the other. They cancel each other and the water is calm. So this is the opposite, where a crest is moving towards a trough. Let's sketch this. So let's just draw a line here. Here we have a crest moving in this direction. Let's say amplitude is A. And over here we have a trough moving in this direction. Now these two are out of phase. Eventually they will have to meet each other. And when they do meet each other, let's say that a trough should be negative A plus negative A will give me 0, so I get this. An area where the amplitude becomes minimum, or we can say the amplitude in this case is 0 because they cancel each other out exactly. Then after that the two waves will continue on their way. This wave will move on and this wave will move on as well. So what we get is destructive interference. To get destructive interference, we must have a crest meeting a trough. And if we get this, we get destructive type interference. Remember, superpose means it is the sum of the displacements. So when they superpose on each other, it's the sum of the displacements of the two waves. If they're in phase, we get constructive, and if they're out of phase, we get destructive. As illustrated, a crest from the left superposes on another trough coming from the right that will cancel each other. There is no resulting disturbance in the medium. This is called destructive interference. The principle of superposition. When two waves interfere, the resulting displacement of the medium, example, the slinky spring, at any location is the algebraic sum of the displacements of the individual waves at that same moment. So when you get principle of superposition, basically what we are saying is the displacement is the sum of the displacements at the place of or point of interference. In the diagram you can see the two waves. Two mechanical waves superposed in photograph A and produce a wave with a higher amplitude, which you can see in photograph B. Observe what happens in photograph A. We can see that the two waves move towards each other. Note that the maximum displacement of the slinky spring is the sum of the amplitudes of the waves in photograph B. So remember your principle of superposition. Your final displacement is the sum of the displacements of the amplitudes of the two waves. At any point, the displacement is the sum of the separate displacements due to each wave. This is called the principle of superposition. Let's try an exercise. In the diagram, we have two waves coming towards each other out of phase. We have a crest and a trough. What happens when a pulse of amplitude A superposed another pulse with amplitude negative 2A from the opposite direction? So if you have a wave of A moving towards a wave of negative 2A, what will be your final displacement? Remember, it's the sum of the two, so just add them up. A plus negative 2A will give you correct. So you should get a trough of value negative A. Let's have a look. Answer: the destructive interference of two waves with different amplitude. Once the two pulses pass through each other, there is still a crest and a trough heading in the same direction which they were heading before interference. For interference to occur, the two interfering waves do not need to have equal amplitude in opposite directions. For example, a crest with amplitude of A unit can meet a trough with amplitude of negative 2A unit. The resultant displacement is negative A unit. Let's try another question. What is the amplitude of the wave formed when a wave with an amplitude A meets another wave with an amplitude 2A? When constructive interference occurs for two superposed waves with amplitude A, what is the amplitude of the waves obtained? So we've got two possible scenarios. First, A is moving towards another crest of 2A. What happens when A meets 2A? What will be your final amplitude? And in the second case, we are saying A and A move towards each other. What will be your final amplitude? Write the two values down. Let's check the answer. Answer. For the first one, when A meets 2A, we'll get an amplitude of 3A. And when A meets A, we get an amplitude of 2A. Now, watching this video, you can see that we have two waves coming down, or two waterfalls, I should say. And from these two waterfalls, we get two sets of circular waves that are interfering with each other. There are two sources of water waves. These two sources of water waves are coherent. Coherent means the two waves have the same phase and the same frequency. It is very important that you understand the definition of coherent, because in order for us to get interference, especially interference with circular waves, we must make sure that our two sources are coherent, meaning they have the same phase and have the same frequency. As both waves move in the same pond, this means that both will have the same speed and thus have the same wavelength. Remember, the two sources of waves must be coherent. So what we get are two waves moving towards each other and they're both circular. Now let's sketch this on the board and have a look at what is going to occur. So let's use this space over here. Let's say we have one source over here and another source over here. This source is producing a set of circular waves. Like so. Over here, from this source, we're getting another set of circular waves coming out. Like so. And then we have another one. Like so. Okay. So what we have are waves that are crossing over each other. Now we need to identify key things in this wave. So let's go through it very nice and slowly. Number one, the distance between the two sources here is known as A. We give it the symbol A. Secondly, look at our wave. These solid lines represent crests. So this here is a crest. In between our crests, we've got one crest here and another crest here. There must be an area for the trough. So this is the trough. Now, as we already understand from what we've done just now, if I get a crest and a crest, or a trough and a trough, I'm going to get constructive interference. Now let's identify some places where we have this. We're looking for crests overlapping with crests or troughs overlapping with troughs. Let's have a look. If we follow here, at this point here, I have a crest crossing a crest. Over here, I will have a trough crossing another trough. Over here, I have a crest crossing a crest. So this whole line up here gives me an area of constructive interference. We call this an antinodal line. So this is the antinode. Remember, antinode represents constructive. Now, destructive interference, as we know it, is a crest meeting a trough. Let's find some of these points. Over here, I have a trough and a crest meeting each other, right there. Over here as well. If I move forward, here I have another crest and trough meeting each other. What I get is a second line going up like this. This line represents an area of destructive interference. We call these nodal lines. So it's the node. So here is the node. And remember, your node represents destructive. Now, if I continue, I can find the next antinode. So if I go along here, I will find trough and trough, crest and crest, trough and trough, and I get a second line here, which is, again, an antinode. The distance between two consecutive lines is represented by the symbol x, meaning the distance from antinode to antinode here, this distance is x. The distance from the source to where I find x, this value here, this is represented by the symbol d. That is the symbol from our source of vibration to where we are measuring x. And remember what x is? It is the distance between two consecutive lines of antinode or two lines of node. Now, if I take these values, a, x, and d, I create a formula which says lambda, the wavelength, equals ax over d. Now, there are some key relationships in this formula that we need to know. The first key relationship is if your x, which is the distance between one antinode and the next antinode, or from one node to the next node, increases, lambda increases. So, relationship number one, if x goes up, lambda will also increase. Another key relationship is the relationship between a and x. These two are inversely proportional to each other. So, if a increases, x decreases. So, if your sources are further apart, then the distance between the nodes or the distance between the antinodes becomes smaller. So these are the key things that we need to notice. So let's quickly recap. The solid lines are crests. In between crests are your troughs. You can identify constructive interference areas, or what we call antinode lines, by looking for these. Crest and crest, trough and trough, crest and crest as they overlap each other. You can find the antinode line by just joining all the points where you get constructive interference. You can also find node lines, which are basically areas of destructive interference. They are where your crest meets your trough. Remember, crest and trough is destructive. So, finally remember, the distance from one consecutive antinode to the next consecutive antinode is represented by the symbol x. The distance between the sources is a, and from a, perpendicular distance to where you measure x is represented by the letter d, capital D. And we finally get the formula lambda equals AX over D. So this is our conditions for constructive and destructive interference when we get two circular waves that are coherent meeting with each other. So, conditions for constructive and destructive interference. The waves from coherent sources have the same frequency, the same wavelength, and constant phase difference. The red lines connect all the bright waves in phase. These lines are called antinodal lines. The lines join point of constructive interference. The black lines with calm water are formed when wave fronts are exactly out of phase. These lines are called nodal lines. The lines join the point of destructive interference. Now, we can also get constructive and destructive interference with light and with sound. With light, what you're going to see is something like this. So with light, what we see are, right in the middle, we get an area of brightness. This is constructive. This is our antinode. This will be followed by an area of darkness, which is destructive interference, followed by another bright area and another dark area, another bright area and another dark area. So we get stripes. The distance from one bright to the next bright is your X, or from a dark to the next dark. Now, we don't call them stripes, we call them fringes. So remember your bright fringes this is your antinode or your area of construction, and the dark fringes these are your nodes or your areas of destructive interference. So remember, you're going to get these dark areas here, and in between them you're going to get lighter areas. Now, a key thing to understand here is the relationship once again between X and lambda. Different colors have different wavelengths, and when we do interference with light, we always use monochromatic light. So let's just make a note here that we must use monochromatic. Monochromatic light means one color only. Now, red light has a long wavelength. So let's put that down here. Red, lambda is long. So if red light has a long wavelength, it means X, this distance, will be greater. So X is greater. And if you use a different colored light, let's say blue, where your wavelength is shorter, it means X will also be a shorter value or a smaller value. So remember, key things with light, we have bright fringes. Oops, excuse me, I forgot the S. We have bright fringes, which are our antinodes. We have dark fringes, which are our nodes. From one fringe to the next consecutive fringe, that is our value for X. Remember, we must use monochromatic light. Different light have different wavelength. If you have a long wavelength, you have a bigger X value. If you have a short wavelength, you will have a smaller X value. Now, what about sound? Even sound has interference. So let's go up here to sound. Now, with sound, what we get are areas of constructive interference. So, constructive interference, what we get is loud sound. And in areas of destructive interference, we get soft sound. From one loud to the next loud area, that will represent your X. And or from one soft area to the next soft area, that also will represent X. So please understand, we have constructive interference with water waves, we have constructive interference with light waves. Remember the key, you must use monochromatic, and we use this term fringes, bright fringes and dark fringes. And with sound, constructive areas or your antinodes are loud, and your destructive, your nodes, are going to be soft. Destructive interference in an aeroplane. Engine noise is disturbing. Microphones pick up engine sound and feed it into a computer. Computer generates sound waves that interfere destructively. The cabin is quieter. So this is an example of using constructive or destructive interference in our daily life. Here we are trying to reduce engine noise in the cabin by destructively interfering it, by creating destructive interference in the cabin by using a computer to generate a sound wave that is out of phase. Let's try a question. Pattern of water wave interference from two sources close to each other. The two photographs taken from the same ripple tank where the distance A, the separation between two sources, are different and the frequency of vibration of the two sources are the same. Analyze the photograph and answer the questions below. So these are the two photographs. As you can see in the first photograph, A is small. The two sources are close to each other. And in the second diagram, A is larger. The two sources are further apart. Are the waves produced by the pair of sources of vibration coherent? Explain. So, are they coherent? Well, think about it. They're both coming from the same source or the same motor. So therefore, they should be coherent because they should have the same frequency and the same phase difference. Answer. The two waves are coherent because the waves are from the same source and vibrating at the same frequency. Now, let's look at the A. In the first diagram, A is small, and in the second diagram, A is a larger value. If the separation of the two sources of vibrations are A1 and A2, what is the relationship between A1 and A2 to the separation of the antinodal lines? So here we want to have a look at our relationship over here. This is the key relationship. If A is increasing, what happens to X? So when you answer the question, keep it simple and keep it down to the relationship. On the side of your paper, write down A increase, X decrease. Now change that into words. When the separation between the sources increases, the distance between two antinodal lines, which is X, will decrease. That's all you need to say. Keep it simple and explain the relationship in terms of increases and decreases, or in terms of directly or inversely proportional. Answer. A is inversely proportional to the separation of the antinodal lines. So, as A increases, X decreases. Let's do a quick summary. State the principle of superposition. The final displacement is the sum of the displacements. Remember that. Explain the interference of waves. If you get a crest and a crest, or a trough and a trough, you get constructive interference. If you get a crest meeting a trough, you get destructive interference. Interpret interference patterns. Remember, if you connect all the areas of construction, you get what we call an antinodal line, antinode. And if you connect all the areas of destructive interference, you get a nodal line, your node. Remember, with light, you're going to get bright fringes for constructive and dark fringes for destructive. And with sound, you get loud areas for constructive interference and soft areas for destructive interference. Remember the relationships in the interference formula. So finally, remember these relationships over here. Your formula is lambda equals AX over D. Remember, if X increases, lambda increases, and if A increases, X decreases. And key to this is remember about light, okay? Especially the relationship between X and lambda. Red light has a bigger wavelength or longer wavelength, therefore X, the distance between the fringes, will be further. Blue light, which has a shorter wavelength, the fringes will be closer to each other. That's all the time we have for this lesson. Thank you for watching ITTV.